Okay, so hi everyone. Looks like only three of us have joined yet. So anyway, I'll be starting with the. Someone else wants to join. Yeah, I'll be starting now. So as always, I'll be as last time also. I will be first going through the week's whatever was taught. I will quickly summarize that, and then I will be solving some questions, sample questions. So this time I would like you to attempt these questions. I would like you to again ask me some questions so that everyone might learn. Okay. Yeah, hello. Mm-hmm. Mm-hmm. दो नोट के बीच में so your question is there are two nodes in and between that you have a dependent source. Yes, you can call it a supernode. So that doesn't matter. So if there is a voltage source in between two nodes, you can call that as a supernode. That's true. Yes, you can do that. Okay, so we'll see that. Okay, once let me go through the presentation today. I'll hear you out. Okay. Okay, fine. So I'll be sharing my screen now. So is it visible? Okay, fine. Okay. Yeah. So hi everyone. So this course, NPTEL course, is basic electrical circuits, and it is being taken by the instructor Dr. Ankush Sharma, who is a professor, who is a faculty from the Department of Electrical Engineering, IIT Kanpur. I myself, I am Mayank Anupam. I am a PhD student and a PMR scholar in the same electrical department of IIT Kanpur. So I will be your tutor for this week. So in week 2, you learned mainly about mesh and node analysis, isn't it? Oh, okay. So this slide quickly summarizes everything that you learned in this week. So you learned about RMS voltages. Okay. So you learned about RMS voltages and currents. You learned about topology, what it is. Also learned about two different kind of very frequent networks, which are star connection and delta connection. You also learned about them. After that, you learned how to solve circuits using mesh analysis as well as node analysis. So both these analysis, they are equivalent. So both of these can be applied independently to the circuits, and you will always be able to solve the circuits. So moving ahead. Okay, so in the first part of the week, you learnt about what is RMS current and voltage. So RMS current equation is given by this expression. So what RMS means? What do you understand by RMS? So can someone unmute and tell me what they understand by RMS? Why do we find RMS values and all? Anyone? Okay, so basically, you see, when you try to calculate power, what do you say? It is V times IT, isn't it? This is what is instantaneous power. Correct. Now you want to find the average power. So average power, when you want to find out, suppose you have some sinusoidal voltage source connected to a resistor like this. Okay. And this is suppose Vt, and the current flowing through it is It. So in this situation, what happens? The current will be equal to what? V of t upon R, right? So the current will be equal so current is this. So basically, when you write instantaneous power after that, this becomes Vt into V of t divided by R. This becomes V square t upon R. So basically, when you want to find out the average power, you integrate this term only as a function of time from 0 to time period, and you divide it by time, the total time that you integrated it in. So when you do that, you see this r will come out of the integral, right? And you will be only integrating this v square term thing. So this is what it is here also. V square, Vrms is this v square term which is integrated, and then it is divided by the time, and then you take the square root. So that we call as root mean square voltage. So the significance of finding out the root mean square is that basically when you want to find out the average power, there basically the expression turns out to be of the form of this Vrms. So you learn about this particular expression, this particular quantity, Vrms and Irms. Yes. Okay, fine. I'll tell you that. So, okay, so when you say instantaneous power, suppose Pi, if I represent instantaneous power by Pi, and there is a time dependence here. So, notice. So, what is PIT? It is defined as voltage into current. Okay. So, this is what is meant by instantaneous power. What is power actually? When you have any voltage source and there is a current flowing through that, the power is equal to what? Current times voltage, isn't it? So basically instantaneous power is what? So at every instant of time, what is the power that it is delivering or consuming? So that is equal to voltage times current. That is what is meant by instantaneous power. The term instantaneous means at every instant, basically each and every instant you are finding out what is the power. So that is why there is a time dependence here. It is a function of time. It is function of time. So it depends upon what time you are calculating this particular power. That is why it is called instantaneous power. Now what is average power? PAVG. It is basically integral of this P instantaneous. Okay. It is the average of this particular average of the instantaneous power. What is meant by average of instantaneous power? Suppose you have a this kind of thing, that you have a voltage source and there is a resistor here, and you and basically you have connected it like this, and current is flowing through here. So basically in this case what is happening, this is a sinusoidal voltage source, isn't it? This is a sinusoidal voltage source. So at some point of time there will be more power that will be dissipated. Some point of time there will be less power. So you have to find, okay, so basically in that case what you need to find it is that what is the average power. You are interested in this. In that case you are interested in knowing the average power, in knowing on an average, if I observe my circuit for a very long time, if I observe the power dissipation in my circuit for a very long time, then what is the average of that power? That is what is meant by average power. So it is the time integral of the instantaneous power divided by the time in which you integrated it. Is that clear? Okay. And now there is apparent power. So that is what I will be telling you about next. So apparent power is what? So okay. Yeah, so you know that average power here is written in this. There is a factor here, cos of theta v minus theta I, where theta v is the phase of what? Phase of voltage source, and theta is what? Phase of the current source. Phase of the current basically. Theta v is the voltage phase, and theta is the current phase. So basically this is the factor which is multiply. Hello. Yeah, hold on a second. I think there are some guys who want to enter. Yeah, fine. Okay. So yeah. So basically there is a factor here. You can see this factor is being multiplied by this V times I. You see this factor here. So this is called as a power factor. So I will be telling you about this factor now. So suppose there is a DC voltage source. Okay, there is a DC voltage source connected to a resistor like this. VDC, and there is a resistor here. Okay, so what is the power dissipated here? VDC times IDC, isn't it? If this is if a current IDC is flowing here, then basically the power dissipation is here is what? VDC times IDC, correct? And this is also average power. This power is constant, isn't it? If you observe this circuit for a very long time, the voltage here is not changing because it is a constant voltage. It is a DC voltage, and current here also will not change. It is also a DC current, isn't it? So the current and voltage both are not changing in this case. So if you find out the time integral of this, if you integrate it with time, with respect to time, to find out the average power, so what will you observe? So this is becoming messy. Hold on a second. I'll explain this thing on a note. Okay. So is this visible? No. I have changed the I have brought another window here. Is that visible? Okay, fine. Sorry. So wait on a second. Yeah. So now is this visible? Correct. So basically, what I am saying is that suppose you have a so you have a voltage source here. Okay, you have a DC voltage source here, and you have a resistor here connected like this. So this is VDC, this is current flowing is IDC. So if this is a DC voltage source, then basically this current will not be changing, isn't it? This voltage also will not be changing. So what is your instantaneous power in that case? Correct, VDC times IDC. Now how do you find average power in this case? You are integrating it between some time, okay, let's call it t, and you are dividing it with that time, isn't it? So when you do that, is this dependent upon time? This VDC and IDC, are these two parameters dependent upon time? Right. So you can take it out of the integral, isn't it? So VDC times IDC comes out of the integral, and you integrate basically dt from 0 to t, which becomes effectively what? This is VDC times IDC times 1 over t into t. So tt cancel, and this simply becomes VDC times IDC. So in this case, what happens is, in the case of a DC source, when everything is DC, when everything is not changing with time, your average power is same as your what? Instantaneous power, isn't it? Correct. So now coming back to the point, suppose you have a you have a sinusoidal source now, and you have a same resistor thing here. Okay, now this will also be sinusoidal, isn't it? This current also will be sinusoidal. Correct. Now when you try to find out the current, what will happen? Current will be sinusoidal, this will be also your average power in that case, what will become? It will become what? V RMS square upon R, isn't it? Or it will become V RMS times I RMS, isn't it? Correct. So in this case also, you see the average power, the expression, basically the average power expression looks almost like the instantaneous power expression, which is equal to what? Vs times Is, isn't it? Here Vs is the voltage source and Is is the current. So Vs times Is and RMS times IRMS. These two equations look almost same. So there is a voltage term here, there is a voltage term here, there is a current term here, there is a current term here. So these two look almost kind of identical or same. Yes. No, in the case of a pure resistor, this is the only thing. Yes, you are true, there is a power factor. So that is what I am coming to next. Okay. So now suppose you have a voltage source, and there is a resistor here, and there is a capacitor here. Okay. Now the current here is suppose Is. Now when you find out the average power in this case, this becomes Vrms times I RMS times some cos of theta v minus theta I, isn't it? This is the expression that you are familiar with. Correct. Correct. Here cos theta is theta v minus theta is here theta v minus theta is equal to 0. So that's why you get this 1. So that is why I didn't mention it here. So now I am mentioning it here because there is a capacitance term, so there is some difference between the current and voltage phase. So that is why we get this power factor here, isn't it? Hello? Yeah. So here what do you see here? This Vrms times Irms times some factor. Okay. So this is the average power in this case. Now this looks very different from your instantaneous, your general power expression V times I, isn't it? This is the general expression that you must have studied in your physics, 12th standard physics and all, everywhere. V times I is the power. But other than these two things, here also there is another factor here. Okay, so this is called the power factor. So this is the factor that is basically what do I say? Yeah. So basically, you would have gotten a pure power out of it if this capacitor would not have been present. But because of this capacitor, what happens is that the total power dissipation in the circuit is not as large as you might think. So this is what this power factor means. Because of this capacitor, some power, the power that you will be seeing, that you feel that you are losing, is not as much as it would have been if this capacitor would have not been present here. So that is why this factor is present here. So what I mean is that suppose you look only at this term, Vrms times Irms. Okay, what is this power? This will be definitely larger than this whole product, isn't it? Because cos theta v minus theta is always less than 1. You remember, right? Cos of anything is always less than 1. Right. So this less than 1 term multiplies with this Vrms times Irms. So which makes this whole quantity less than Vrms times Irms. So what I mean to say is that the whole power that will be dissipated in your circuit will be less than the power that would have been dissipated if this capacitor was not present here. Are you getting my point now? Okay. So with that, now let me come back to the slide. Yes. So in any circuit, what happens is that when you say that okay, so in any circuit you must have heard that capacitor does not consume any power. You have heard that, right? You must have heard that somewhere. If you have not heard, then it's okay. So that I will explain now. So when you talk about any circuit, the power is always dissipated only in the resistor. Okay, if there is a resistive element, only that can consume power. And if there is a voltage source or a source or a current source or a voltage source, whatever it is, so if that is there, then that will be delivering power. Okay, here what is happening, this capacitor is not consuming any power. Whatever power is being generated here is completely consumed by the resistor here. So this P average that I have found out here, this whole expression, is the power generated by the voltage source, and it is also the power that is being dissipated by the current source, since the capacitor will not consume any power. Hence this yes, right. Right. I didn't follow your point. What you are saying? Okay, this is I1. Correct. Yeah, definitely, yes. True. So when you do this, you will see that this will become 0. Okay. So this will be Vs RMS times I1 RMS. That's all. And this will be exactly same as this quantity here. True, you are exactly right. Yes, that will happen. Okay. Okay, now so let me come back to the point that I was trying to make. Okay. Okay, so 1 second. Yeah, so I was here, right? So basically in this expression of p, sorry, yeah, in this expression for p, this is the average power. You see there is a Vrms times Irms times cos theta v minus theta I. So this is basically power factor, and everything and this Vrms times Irms is referred to as the apparent power. Why apparent power? Because if in general, what do you understand? What equation does come to your mind when you say power dissipation? It is V times I, isn't it? So basically, if you simply multiply the current times voltage, this is also some kind of a power, isn't it? Hello, right? So this is also some kind of a power, but this is not the actual power that is dissipated in the circuit. The actual power is what? We have to multiply this power factor. So this is the apparent power. You feel that this much power has been dissipated or generated, but actual power is what? You have to also multiply it, multiply this power factor. This is only apparent. What do you mean by what do you understand by this word apparent? Apparent is something which you feel this exists. It might not exist. This is apparent. This is just a feeling kind of a thing. It might not be real. So that is what you might feel. You will have a feeling that this much power is dissipated, but in actual what? Actually, there is a power factor involved here. So now do you understand what is apparent power, average power, and the instantaneous power? No, average power is not called active power. Active power is different. Active power is something which is not actually dissipated. It is actually a power exchange that is going on always between um, the reactive elements. Okay, sorry. Average power is called as active power. You are saying. Okay, so that term. One second. So average power and active power. I have not heard the term active power. I have heard the term reactive power. Okay, so reactive power is what I will tell you. So reactive power is what? Reactive power is the, yeah. You tell me what is reactive power. Correct. And what does it represent? What is its physical significance? What does it represent? Okay, so basically the reactive power is what? It is V times I times sine of theta V minus theta, isn't it? V RMS times I RMS times sine theta V minus theta I. So the term reactive power means what? It is not actual power. It is not at all dissipated. This power is not dissipated in the circuit. Okay, this is just a power exchange that is going on between the reactive elements and your voltage source or your current source. So I just told you now, right, that any capacitor or inductor does not dissipate any power at all, isn't it? So basically, but there is a current flowing, isn't it? If you find out in a inductor or capacitor, there is always a current flowing there. But so basically, if you find out V times I, you will get some instantaneous power there also. So what is happening there? So in order to so what is happening here there is that if you do the calculation, you will find out that in half cycle of the sinusoid, the power is being delivered to the reactive element, and another half cycle of the sinusoid, the power is being delivered by the reactive element. So in half cycle the reactive element dissipates power, in other half cycle the reactive element generates power. So that is why we say that there is an exchange of power that is going on between the reactive element and the power source. And that this reactive power, that the expression for which is Vrms times Irms times sine theta v minus theta I, actually represents that exchange. That is a reactive power, that is not a real power, that is just being that is just an exchange of power that is going on. That is not a real power, that is not being dissipated anywhere. Right. Correct. Right. So basically that exchange. So in one half cycle there is a power dissipation, in another half cycle there is a power generation. So that is constantly being exchanged, right? So there is no power dissipation, so there is no power surplus anywhere. Whatever you are giving it, it is giving it back, isn't it? So that there is an exchange going on always, isn't it? So that exchange is being represented by that reactive power, sine theta v minus theta I into Vrms times Irms. Active power, I have not heard that term, so hold on, either I will tell you today, or I will tell you in the next class. So it's already long and we are already only on the first slide, so I have a lot of things to cover. Okay. So fine. So this I already talked about in the last class also, last week session also. So these are some of the expressions that you already are familiar with. So in a resistor, the voltage current relationship is like this. In a inductor it is of this kind, and capacitor it is of this kind. Now also we also talked about the notion of impedance, or a complex resistance kind of quantity. I am saying kind of because it is not actually how it is, what it is supposed to mean. It is complex. This is Z. This impedance thing, this is represented by Z, and it can be complex. And with this, if we introduce this notion, then we can always write voltage current relationships in terms of Ohm's law. So that is why we introduced this notion. After that, we also said that if you find out the inverse of this impedance, you will get admittance. So moving ahead. Yes. Yeah, so when you do the conjugate, so you know that the current power, average power is given by what? So one second. One second, okay. Okay, fine. So so average power is what? Vrms times Irms times cos theta v minus theta I. So this conjugate thing, this complex power thing, this is just this is something which we just introduced to make our life easier. Okay, this is not something real or anything real about it. We have just made it up to make our life easier. It's just a mathematical convenience that we have introduced in order to make our life easier. Okay, when you say that power is, when you talk about complex power, which is P is equal to V times I conjugate. So if you write it in terms of your Cartesian coordinates, what will you get? You will get V times I times V RMS Here it will be VRMS, IRMS. Hold on a second. Is my screen visible? Okay, fine. Yeah, so when we talk about average power, when we talk about the complex power, it is what? P is equal to V RMS times I RMS conjugate, isn't it? Something of this kind, right? So, yeah. So when you introduced this notion of complex power, this was just for your mathematical convenience. It is not something which is real. It's just a mathematical convenience that you introduced this term. Okay, so when you write it in terms of Cartesian coordinates, you get what? P is equal to V RMS times I RMS times cos of theta V minus theta I, because there is a conjugate here, isn't it? Plus J times sine of theta V minus theta I, isn't it? Okay, so let me change this. I'll again go back to my notes again. Here it becomes messy. Yeah, is this screen visible again? Yeah. So okay, so basically when I tell, average power is what? It is VRMS times IRMS, isn't it? Times cos of theta V minus theta I, right? Now complex power is what? VRMS times IRMS conjugate. And when you will expand this, what is VRMS? VRMS times IRMS conjugate is what? It is equal to VRMS times IRMS mod of all of this times cos of theta V minus theta I plus J sine of theta V minus theta I, isn't it? Right, true. So if you represent VRMS in its polar coordinates, then what will you get? Is it right? This is polar form, isn't it? E to the power j theta V. Okay, so let's say that. Okay, so yeah, VRMS magnitude angle of theta V, isn't it? This is also polar form only. This is shorthand of that. This is polar form. Okay, this is the polar form. This is shorthand. It's just shorthand. Okay. So when you say VRMS, so when you write it in this form, what does it represent? It represents this term only. It is a magnitude times e to the power j theta V, isn't it? Now, what is IRMS conjugate? It is IRMS magnitude conjugate magnitude times e to the power j minus theta I, isn't it? There will be minus theta I. It will not be plus theta I. It will be minus theta I because of the conjugate. Right? Now when you multiply both of these, what will happen? You will see what? E to the power j theta V minus theta I will come together. Right? And then you will expand that, then you will get this term. Cos theta V minus theta I plus j sin theta V minus theta I. Right? So is this clear now? Where? हाँ नहीं प्लस नहीं माइनस होगा why? Okay, so you do it. Okay, so you do it and you will see that it is true. It is indeed true. Okay. Now, so basically, I was telling that this is the total power. This is the complex power. It is given by this particular expression. Now, what is the and what is the real power? This average power, this is the real power dissipated, right? This is the average power. So in this average power expression you can see that this at least this much is representing average power, right? Real power, true. So if you represent it, it will be real plus J times some active, sorry, reactive, isn't it? So this J sin theta times V, so this term is actually representing reactive power, and this first term is representing real power, isn't it? Right. So what did you what is the conclusion then? This power, if you write it in this manner, in a complex form, so you will be kind of compressing all the information in a very small, two quantity kind of a thing. Otherwise you would have been writing like this long expression, something of this kind. If you want to represent the total power, reactive as well as the real power, you will need to write this whole expression, big expression. So what did you do? You simply managed to write it in a very small manner, so that it becomes easier to handle. So that is why you introduce this term P, this complex power is equal to Vrms times Irms conjugate. If you take conjugate here, then you will not be able to match these two terms. So the whole purpose of defining this complex power is to make our life easier. Okay, this cos theta v minus theta I should come here, otherwise we will not be able to make any use of this. So for that we made Irms conjugate. Is it making sense? Right. If the circuit is, if there is a question of calculating total power, then you will have to calculate average power. But in general, it will be written there to calculate real power. But yeah, so if nothing is given, then you need to calculate real power only, average power, which is okay, fine. So moving ahead, okay. Yeah, so we are running late, very late. Okay, so I thought I would be going through this, but okay, I'll just quickly skim through this. So basically, you also learned about networks and circuits, right? Okay, so you also learned about this notion of network and circuit, the difference between network and circuit. So in the last week also I mentioned that a circuit is a network which should have at least one or more loops in it. Otherwise, it is not considered as a circuit, because if there is no loop in the circuit, then basically there is no current flowing through it. So it's just nothing is fancy about it. It's just simple network, and we will not be concerned about such a network where there is no current flowing through it. So that is the difference between a network and a circuit. Okay, fine. So moving ahead, what is topology? So topology, I guess you understood it, understood this term topology. Moving ahead, branch, you understood what is branch. Anyone has any doubt in this term branch? Okay. So anyone has any difficulty understanding nodes? What is a node? What is a loop? Okay, fine. Moving ahead. Yeah. So this is important. So after learning all those things, you learned about some very frequent kind of network connections. Why do I say frequent? Because they are generally seen. They are seen quite a lot in the network theory, in a general practical applications also. These kind of networks are seen again and again. So it will be interesting to learn. It will be interesting to learn them. It will also be convenient for your future if you learn these networks in detail. So one of those networks is what? It is a star connection network. So do you understand the reason that it is called a star connection? Why it is called a star connection network? Correct, right. It is looking like a star, right? So that is why it is called a star connection. Again, this is exactly same as this connection, isn't it? but this is not looking anything like a star. So that is why what it is called T connection. You understand why it is called a T connection? Because it is looking like a T. So topology wise, both of these are same. They are exactly same. There's the connection wise, both of these are exactly same. It's just that you have twisted it in some manner and said that okay, this is star connection, this is T connection, isn't it? So connection wise both are same. So that is why I have given here slash here. So you can either call it a star connection or a Y connection or a T connection. So why is it called a Y connection? Correct. It is looking like a Y. That is why it can also be called as a Y connection, isn't it? So I guess you don't have no one has any doubt in this connection, at least understands the term. Everyone understands the term and the reason behind introducing or defining such a term, isn't it? Okay, fine. Moving ahead. Now coming to the next very common kind of topology. It's a delta or pi connection. So can you tell me why is it called delta connection? Yeah, so here it is shown in the form of inverted delta, but what is a delta? Delta look like? This is the shape of delta, right? Right. So basically this is delta connection. It also can be, if you twist it slightly, you can also basically make it in this form, make it look like in this form, isn't it? But this here looks like what? Correct. This looks like a pi. So this is also called a pi connection. So that is why I have given here slash here. So this is either delta or pi connection. Both mean the same thing. Okay, moving ahead. Yeah, so this is very important. So you should be able to convert delta to star and star to delta, right? So for that there was a messy derivation for that, and the final result is very simple. So if you want to convert a star connection to a delta connection, if you want to find out the equivalent resistors, so you are given a star connection like this. There is a resistor here like this, then there is a resistor here like this, there is a resistor here like this. You are given 3 resistors and you want to find out, and you also, okay, so basically there are 3 resistors and there are 3 terminals also, isn't it? This is terminal 1, this is terminal 2, this is terminal 3. These 3 are the 3 terminals of this connection, star connection. And you want to find out what is the equivalent delta connection. So what is meant by, okay, so this is, suppose this is the delta connection, and this also has the 3 terminals coming out of it. This is 1 prime, this is 2 prime, this is 3 prime. So basically you want to find out what is the, basically you want to find out what are the these 3 resistors RA, RB, RC in terms of R1, R2 and R3, such that their terminal characteristics remain the same. So what do you understand when I say I want to find equivalent of something? What do you understand by this term? Okay, so yeah, so you are almost right. So can you please elaborate what do you mean by that? Okay, so you have a, so suppose this is a network. Okay, this is a network, there is a lot of resistance in it, there is some lot of resistance in it. So what are you saying that you want to replace it with a single resistor? Okay, so yeah, so you are understanding it in only one, you are limiting your understanding to only one particular application of equivalence. So this equivalent business is a very important thing. You should understand the concept of equivalence. So what to understand by equivalent is, suppose in general you have a, suppose this is a box. Okay, there are a lot of things inside this box, a lot of resistors, capacitors, a lot of things in this box, but out of this box you have these terminals coming out. Okay, so you do not know what is inside this block. You are following me? Such a box we say that it is a black box, because you cannot see inside this block. All that is accessible to you are these terminals which are coming out of the box. You understand what I am saying? Okay. So this is just like Jadoo ka pitara. Okay, you don't want to open it. You have something. You have some connections out of it. You just know that these are the connections. Only those wires are accessible to you. You cannot see anything inside of that pitara. Okay, this is band. This is just closed. You cannot access those things. So such a box is called black box. So suppose there are a lot of things inside this black box. You do not know what they are. Okay, all you know that there are some terminals coming out of it like this. Now the purpose of finding equivalent is that when you say something, it can be replaced by an equivalent. Suppose a resistor. Oh shit. Okay, hold on. Okay, sorry. Okay, connections. Yeah, so I was talking about the black box. There are resistors, capacitors inside this, there are inductors and all. So out of this, only these terminals are coming out. This is called a black box. So there are these terminals coming out. So suppose you want to replace it with an equivalent. Let's say that is only a resistor equivalent. Okay. Suppose you want to replace it with this equivalent. Well, let's call it R equivalent. So what it means is that if you are connecting some voltage here, okay, hello, everyone is with me? Yeah. So what is meant by finding equivalent is that if you are connecting a voltage at each and every terminal, okay, here, for each and every terminal you are connecting a voltage, okay, each and every terminal you are connecting a voltage here, and you are measuring what is the current here, okay. Suppose this is I1, this is I2, this is I3. You are connecting a voltage source for each and every terminal and you are measuring what is the current. Okay. Now, if you are replacing it with some equivalent, then that same relationship should hold here also. So basically, this equivalent cannot be a single terminal device. First of all, there should be as many terminals in this equivalent as there were in the earlier original circuit. So if there are 5 terminals here in this circuit, so whatever equivalent you will find, you should also have 5 terminals here also. Okay, first thing. Now second thing, if these voltage sources, if the same voltage sources are connected here also in the equivalent, you should get the same current flowing through the same terminals. That is what is meant by equivalent. Are you clear on this? Right. So when you say you want to find out the equivalent of this star connection in the form of a delta connection, it means that there are 3 terminals. As I showed, there are 3 terminals in the star connection. So this is, so these three dots, these 3 represent 3 terminals, isn't it? And this here is a delta connection like this. So when you say that these 2 are equivalent, it means that if you connect voltage source here, some voltage source here, and some voltage source in between these, and if you want to measure the current out of all these 3 voltage sources, they should be exact, and the same thing you do here also. You connect the same voltage source. If it is V, it should also be V. The same voltage should be same across all. And okay, and you also connect some voltage source here, and you also connect some voltage source here. Now if you find the current here also, they should all be the same. Understood? Only then can you say that these two networks are equivalent. Did you understand? Okay. So if you do not, then just ask me, because this is a very important concept of equivalence. It will be used across different domains also. If you go to any domain like electronics or whatever, so this equivalent thing is very important concept. So a lot of people misunderstand this equivalent thing. Yes. Yeah, yeah. So that will become, no, if you have a resistor, if you have a capacitor and inductor, the equivalent will also contain either a capacitor or an inductor. Otherwise you cannot obtain an equivalent circuit without any inductor or capacitor if you have an inductor capacitor in the original circuit. Of course you can do that. Why not? Right. You have to replace this R with the Z. You have to replace here R with Z. Okay. And then you will, yeah. And if you replace R with Z, you will get the same expression. And with that Z you can use either for R or j omega L or 1 over j omega C, isn't it? Right. Correct. Correct. So, okay. So I was saying. So you understood the term what the term equivalent means, isn't it? Correct. So that is the concept behind finding equivalents. And as so you already learnt in the week that the equivalent of this is given by this expression. So I will not go into derivation. That is quite a messy derivation, and it is already there in the lectures. So if you have any doubts, you can go through that derivation. So this is how it is found out. So but the motive behind going through this part was to explain you what the term equivalent means. So this equivalent, the understanding that I want from you is what I told you today. So equivalent means if you want to find the equivalent of a particular network, then basically the current voltage relationship should hold the same for both the networks. Okay. If you found out an equivalent for a network, then basically the voltage current relationship in the original network and the equivalent network should be same. It should not differ. Okay. Okay, fine. Okay, so anyway I have gone above time. I think it's already 54 minutes. So I thought of covering a lot of things today, but unfortunately I'm not able to. So fine. Do other guys have other classes? Hello? Do any one of you have any other classes here? Fine. Okay, fine. So, okay, I'll take another 5 minutes and cover whatever I can. Then I'll cover the other things in the next week. So moving ahead. So okay, so this is the delta to star conversion. So basically, this is also the same thing. We just if you have any doubts, you go through the derivation that is there in the lectures. So this was also explained quite very well. There is a quite a messy derivation here also. And if you have a delta connection network and you want to find the star connection, so here is a delta connection like this, and you want to find out the star of this, then basically you need to apply this formula here. Moving ahead. Okay, moving to the mesh analysis. So I don't think there is enough time to complete this part here. Let's leave it. I will try to cover this in the next week. Is it fine with everyone? So it will actually it's quite long, so it will take a long time for me to finish it. If I start it, then basically it will be useless if I leave it midway. I have to again do the same thing in the next class also. Okay, so thank you guys. So next time I will try to keep track of the time. So this time I lost track of the time, and so sorry for that. Next time onwards I will try to keep track of the time. Okay, thank you for joining everyone, and also try to join the next week. I will cover all these things that I left today, and also cover the next week's topics also. Okay, thank you guys. Thank you for joining.